All right, greetings everyone. Welcome to the second part of the video for section 7.2. And in this video, we'll be continuing on looking at using those same identities that we used in the first video. So as a reminder, the identities we're working with, the sum and difference identities, are these ones here. As I said in the previous video, you do not necessarily have to memorize these. However, it will be important that you're familiar with them, and mostly important with or familiar with using them. Okay. All right, so let's look at an example of using these identities to prove another set of identities. So we haven't done this for a while, but here we're given sine of x plus y minus sine of x minus y. We have to prove that that's equal to 2 times cosine of x times sine of y. Now, as we've talked about in the past, there are lots of different ways to approach a problem like this, but one of the usually tried and true ways is to choose one side and make it equal to the other one. In this case, I'm going to choose the left-hand side and try to make that equal to the right-hand side, which, as we've seen, is generally a winning strategy. Okay, the next thing that you may notice is that each of these things on the left-hand side, so the sine of x plus y and sine of x minus y, they look kind of like things from the previous slides, so we can probably use some of those identities. So for example, on the first one there, we have sine of x plus y. Well, that looks like the sine of alpha plus beta. And using that identity that we have, we can rewrite that as sine of x times cosine of y. I apologize that these letters are not all showing up. There we go. Plus cosine of x times sine of y. Okay, so that is the first part. And then we're going to subtract, and we want to be very careful here. It's minus what we're going to put in for the interval or the identity for sine of x minus y. So we're actually going to put parentheses around that. Otherwise, this will throw our answer off. And so we can rewrite sine of x minus y according to our identity as sine of x times cosine of y minus cosine of x times sine of y. Okay. And you probably noticed looking at this, it looks like there's some like terms, right? I see cosine of x, sine of y there and there, sine of x, cosine of y there. So that seems like a good sign. But before we can deal with combining any like terms, we have to deal with that negative sign on the outside of our parentheses, which means it needs to be distributed in to our two terms inside the parentheses. So then we can rewrite the whole expression based on that. So I have sine of x times cosine of y plus cosine of x times sine of y. We distribute the negative sign there, we'll get negative sine of x cosine of y, and distributing to the second term will actually give us a plus cosine of x times sine of y. So now we've got everything out of parentheses, so we'll look at our like terms now. And I see a sine of x cosine of y here, but then a minus sine of x cosine of y there, so those will cancel. And I have a cosine of x sine of y plus another cosine of x sine of y, which then gives us 2 cosine of x sine of y, which if we look up above, that's what we were trying to come up with, right? So now we're done, and we've proved this identity. Woohoo! Go us, right? Yeah. Okay, let's look at the next problem. So now we're going to be asked to solve an equation using this identity, or these sets of identities here. Okay, so notice we're given sine of 3x times cosine of 6x minus cosine of 3x times sine of 6x equals negative 0.9. We're asked to solve that on the interval 0 to 2 pi, which at first this probably looks like a whole lot of nonsense, right? Because we've got cosines and sines, and they've got different things on the inside, so we can't factor things, and nothing's squared, so we can't use our Pythagorean identity. And Cody, it just causes me a lot of anxiety. Well, don't worry, y'all. We can handle this. Because we also note that if we think of 3x as alpha and 6x as beta, and this is alpha and beta, well, it looks like this matches the identity for sine of alpha minus beta. Okay. So what that tells us then is we can rewrite this instead of this big long thing with sines and cosines. We can rewrite it as sine of what we have for alpha, which is 3x, minus what we have for beta, which is 6x, equals negative 0.9, which then the inside there can simplify, so that sine of 3x minus 6x will become negative 3x equals negative 0.9. And now we're in business, right? This looks more like something that we've used before. Okay, and at this point, normally we would use a U substitution. But before we do that, I'm going to use some other identities. So you may recall from chapter 6, we had our negative angle identities, which said that if we had the sine of negative theta, that's equal to negative sine of theta. So I'm going to use that here since we have this negative on the inside. So that tells us we can more or less move the negative sign to the outside. So this will become negative sine of 3x equals negative 0.9. And then we can actually get rid of that negative sign by dividing both sides by negative 1. And when we do that, we'll be left with sine of 3x equals positive 0.9. Okay, and so then we'll go on to solve that from there. So I'm going to go ahead and clear this out. So we are working again with sine of positive 3x equals 0.9. Now we can use our U substitution for the stuff inside of the trig function. So we'll say U equals 3x. So this then becomes sine of U equals 0.9. Since 0.9 is not a value that appears on the unit circle, we can find a value for U by doing inverse sine. Okay, and we're working in radians since the interval we're solving is 0 to 2 pi. So when we do inverse sine of 0.9, we get 1.11, looks like 20, which if we think about our quadrants in unit circle, since we took the inverse sine of a positive number, that's going to give us an answer in the first quadrant. And because we're finding answers on the interval 0 to 2 pi, we should have a second answer somewhere where sine is also positive, which in this case would be in the second quadrant. And we know that because our answer here is in the first quadrant, that it's also equal to the reference angle there, which is going to give us our reference angle for the second angle. So that will also be 1.1120. And so to find this angle in the second quadrant, that means since it's 1.1120 radians back from pi, we can do pi minus that to find the second answer, which then gives us 2.0218. So 2.0218. So now we have our two answers for U. But remember, we're not solving for U, we're solving for X from up here. So since these are answers for U, We can now set up an equation where each of those is equal to 3x. So if 3x equals 1.1120 and 3x equals 2.0218. And then in each case, we divide by 3 to isolate the x. And when we do that, let's see, do 1.1120 divided by 3 gives us 0.3707 as our first answer, and 2.0218 divided by 3 gives us 0.6739 as our second answer. Okay. And there we go. All right, that's it for now. Thank you for watching.